Hello everyone and welcome to another video. In our previous videos, we've covered the concept of derivatives, learning how to solve them and differentiated them using different functions. But today, we're going to take this one step further and see how we can apply derivatives to solve real-world problems. So, let's get right to it. In today's lesson, we're going to be diving into optimization problems. And we're going to solve for the maximum area of a fixed perimeter, which is basically the typical fence problem. So we have 100 meters of fencing, 100 meters of fencing. And we, in a rectangular area, and we want to find the maximum area that we can enclose using these 100 meters of fencing. So we solve this using derivatives. First of all, let's define our variables. We have x and y. Let's write these down. Variables. Let's call x the length of the rectangle, and let's call our y the width of our rectangle. Let's also apply some restrictions. Our restrictions are basically that neither our x and our y can be greater than 100 meters. So x and y have to be smaller than 100, as obviously if they weren't, we wouldn't be able to do a rectangle. So let's write our auxiliary equation. Auxiliary equation. In this equation, what we need to do is write what we know. So we have 1x and 2x's, and we have 1y and 2y's. So this is a rectangle. So we know that 2x plus 2y must be equal to 100. The perimeter must be equal to 100. And now let's write our optimization function. Finally, we're left with our optimization function. This is the area we want to find that has to be maximized. Well, our optimization function is going to be our area, let's call it A, based on our x and y, both of our variables. And this is going to be x times y, of course, that is how we find our area, and we want this to be maximized. We want this to the max. So now that we have our auxiliary equation and our optimization function, we need to get our optimization function to only be using one variable, as we only need one to solve with derivatives to optimize for the maximum area. So what we're going to do is take our auxiliary equation and substitute by isolating y. So we're going to do 2y is equal to 100 minus 2x. And therefore, y is equal to 100 minus 2x over 2, which can be further simplified as 100 over 250 minus 2x over 2 minus x. And now we're going to write that our optimization function is in terms of x. We substitute what we have, y equal to this, into our y. So we have x times 50 minus x is our optimization function. We can continue solving this. Minus x squared plus 50x. And now we use our derivative in order to find our maximum. We derive our function. This is going to give us minus x squared is minus 2x plus 50. And now all we have to do is equal this to 0. We forcefully equal this function to 0. We say that minus 2x plus 50 is equal to 0. Therefore, 2x is equal to 50. We move this to the other side. And x is equal to 50 over 2, which is 25. And this is our answer for x. The length of our triangle to be maximized must be 25 meters. And this is done because if we equal our derivative to x, we haven't seen this yet, but you will understand further. This means that if our function is whatever, what this means is that we have a local maximum at x equal 25, that our function might do something like the following. And when this is equal to 25, we have a local maximum in our function. As we equal it to 0, this means that in a derivative, your function will do whatever, but it will cross at x equal to 25, the x-axis. When your derivative is equal to 0, you will have a local maximum in your original function. And that is why we know that x equal to 25 is the maximum. Now to find for y, we just do 50 minus x, 50 minus 25, which is equal to 25 as well. So, to maximize the area of your rectangle with only 100 meters, your length has to be of 25 meters and your height of 25 meters as well. Thank you for watching. I hope you have understood. And next video, we're going to be practicing with another example of optimization.